It is Ilke Arslan out of the Center for Nanoscale Materials at Argonne National Lab. And we gets connected up here. She's going to be presenting on understanding catalysts using advanced methods in transmission electron microscopes. In the transmission electron microscope. Can't read.
Excellent. Well, thank you so much for the introduction, and I would like to thank the organizers for inviting me. It's very exciting to be back at a conference in person. So nice to see you all. So we have seen some beautiful images today, this morning, of catalysts and catalyst particles and atomic structures. And I'd like to give you just overview and kind of zoom out a little bit. I won't go into much detail in any of these areas, but give you some other things to think about in terms of characterization of catalysts. So the first one will be three-dimensional imaging. We've seen some of that with the previous talk with X-ray. The second example is going to be in situ liquid imaging. We've seen a lot of gas imaging, but what about those catalysts in liquid, for example, zeolites that we want to try to grow? And lastly, in situ in the fourth dimension, which is time, to look at ultrafast electron microscopy. So let's go ahead and start with tomography. You've been looking at STEM images all morning, and you may or may not know the difference, but STEM is scanning transmission electron microscopy, different from standard TEM in that you focus the probe and scan it across the specimen surface. You can see my arrow there. And the reason why this is important for catalysis is because this image gives you its scattering. The electrons are detected on this high angle detector here. So you get scattering at high angles, and it's proportional to the square of the atomic number, the element. So for catalysts, this is important because if you have platinum on a zeolite, the platinum will light up. So you don't need chemical analysis in addition to just your imaging in order to be able to differentiate what the materials are if they are far enough apart on the periodic table. Another reason why this is important is because it's incoherent imaging, which is important for electron tomography. When you take images at lots of different tilt angles, you need the contrast to not change. In a regular TEM with phase contrast imaging, you can have different contrast at different tilt angles. And this does not give you a viable reconstruction, 3D reconstruction. So STEM is the way to go for 3D imaging. And finally, for in situ liquid imaging, if you have a TEM where you're just chunking all the electrons down at the same time, you can get bubbling and lots of beam effects that you don't want to see. The small focus probe of the STEM, as it moves across the windows with the liquid in there, it naturally dissipates the energy so that we don't see that bubbling unless you put, again, a lot of electrons in there. So why do we need 3D imaging? Hopefully I don't have to convince any of you about this, but the images that we've been looking at this morning are 2D projections. That's what we see in a TEM. So we have these three-dimensional catalyst particles that we've been looking at this morning, but what we're doing is we're just taking a projection image of that. So what's happening on the 3D morphology of the particle can be very different than what we are seeing in our projection image. For atomic resolution, obviously it works very well, but if you're looking at nanostructure, nanoscale, it can be very different. So what we did here was, in order to do tomography, as I mentioned, you have to take a lot of different images at a lot of different angles and then reconstruct those images into a 3D tomogram. It is very difficult to do this, if not impossible, in an in situ gas holder. And the reason for that is that you can't tilt high enough to get the information that you need for the tomograms. So we need to tilt to roughly 70 or 75 degrees in both directions, at least every 2 degrees, in order to get a good reconstruction. With the in situ stages, you are limited by the 2 windows, and as you start tilting, it gets very thick, you can't see, and you can't get up to 70 degrees with in situ holders usually. So what we did was use this ex situ gas station in order to reduce the catalyst And then we sealed it with an O-ring and without exposure to air took it back to the microscope and did tomography on these particles before and after. So these are Fischer-Tropsch catalysts. They're cobalt on alumina. And here is an image on the left before reduction. And you can see the image on the right after 15 minutes of reduction at 400 degrees C in that ex situ chamber I just showed you. How can we tell if by looking at these two images, you wouldn't be able to tell whether the catalyst has been reduced or not? So we can use electron energy loss spectroscopy in the microscope to detect that. And the way we do that, you can do it from the cobalt L3 to L2 ratio, but it's much more obvious in this pre-peak of the oxygen K edge. And we tested this at different times, reducing for different times. And so we are confident that we have reduced as much as possible to a cobalt metal. So let's look at now, let me go back, and you've seen these two images, and it's very difficult to say what's going on with the distribution of cobalt oxide where the cobalt is after reduction. But when we go to 3 dimensions, you can see the alumina is represented in red and the cobalt is represented in green. And on the left, you're looking at before reduction, and on the right, you're looking at after reduction. It might be a little bit difficult to see because of the alumina. So if we go ahead and remove the alumina and just look at the cobalt side on the left and the cobalt reduced metal on the right, now you can really see what the differences are and how the cobalt has moved. It's surprising to us that it has moved quite good distance out, and a lot of the smaller particles have moved to surfaces. So let's take a look at this little section here to see the differences a little bit better. So again, this is before and after reduction of that very same volume of material. We have determined that the cobalt particles, the spheres, the alumina pores, are 3 to 4 nanometer spheres, and then there are these other structures that are 7 to 8 nanometer kind of more flat morphology pores. And we've confirmed that that stays the same before and after reduction, which is good. But the size of the cobalt particles and the distribution of the cobalt is different. So if I play this movie, you can see all of these little bubbles here. Those are the pores in the alumina structure. But you can see that the distribution of the cobalt oxide on the left versus the cobalt reduced metal on the right is different. And let me show that to you in one more movie. So the alumina has been removed now, the support has been removed. This is just in red, cobalt oxide, and then in yellow, the reduced cobalt metal. So you can see very clearly here that all of these small red particles, they have gone out towards the surfaces, and that makes sense to us because the surfaces are going to be more catalytically active, but it's just a surprise that they have moved so far. Okay, so I'm going to move on now to in situ liquid imaging. So a lot of what we do in the microscope in terms of liquid imaging is usually done at room temperature. And here's an example of that. If we take a palladium surfactant, a palladium material in a surfactant, and it's this sludge kind of material that you see here. And we want to try to grow particles inside the microscope to see how palladium particles, porous palladium particles grow. This is a dark field and bright field pair. So just 2 detectors imaging the same thing at the same time. You can see these 2.5 nanometer size particles coming together and forming these larger 5 nanometer particles. So this is kind of like the beginning stages of what's happening. The smaller particles are coalescing into larger particles. And then a little bit later, we see these clusters of the larger particles coming together and trying to form and combine with one another. The reason why they can't do it quite well is because the surfactant is in there. And so that's how you get the porous structure. And in the end, these are the particles, these porous nanoparticles are what we grow inside the microscope, which look like the particles grown outside of the microscope. So that's great when you're looking at things at room temperature. But now, if you want to try to understand how a zeolite forms, you need to try to do that at elevated temperatures, and you need to try to do that at pHs that are not normal either. So it's kind of electron microscopy suicide to put this into your microscope. The pHs here are around between 11 and 13, and the temperatures were able to go up to 100 degrees C. The experiment I'll show you is at 70 degrees C. The heating is done through these chips, through these gold, the gold pads throughout. And what we're imaging is this very slit, the dark blue slit there in the middle. That's where we image from. So what we decided to look at was zeolite Y because it has a lower temperature formation, lower pressure formation, a fast formation, no organics, and we could correlate it with other methods as well that we were looking at. So these are just some more details of the gel composition if you're interested. So when we first put this into the microscope in the liquid stage, what we see are all of these uniform gel particles. These are silica particles, 8 to 10 nanometers in diameter. And we've been talking about the effects of the electron beam. And here you can see that at a dose of 1690 electrons per nanometer squared versus 1130 electrons nanometer squared, it's not a huge difference, but there is a critical point at which the electrons play a role. So let me run this movie quickly so that you can see that in the beginning, these particles look similar to these particles. But as time goes by, they lose their spherical nature and they become in these other shapes, and they come together a little bit more. They grow a little bit and they combine a little bit. But when you reduce the electron dose, and this is with no heating, no temperature, you can see that the particles remain the same over this 8-minute movie. You can see this guy right here is doing a little Brownian motion walk, but nothing is happening. There's no reactions happening. There's nothing happening with the change in the particles. I'm having a hard time getting the movie to, it's the wheel of death. Okay. This is what happens when you have big movies. All right. So now what happens when we heat it up to 70 degrees C and we do our in situ synthesis. And I put it in these inverted commas because it's not the same as a synthesis that we do for catalysis, but it's the closest we can get, right? So hopefully I don't have the wheel of death again here, but what you see are these gel particles. There's a lot more movement now, and I'm going to speed this up in just a second, but I want to point out a couple of things. These particles outside of those 8 to 10 nanometer gel particles that I showed you in the beginning, they are growing. And there are some of these that will grow out of solution. So if you look sort of in this area, as I speed up the movie, you see something forming out of quote nowhere. So there's that particle that starts growing. My computer doesn't like me doing this. Oh, it's the wheel of death again. So basically what we are observing is the zeolite formation from the solution. And it is not, as this movie shows, it is not related specifically to the precursor particles that are already in there, but they have an effect, obviously, with everything else that's in the gel solution, but that the zeolite particles are growing out of solution. And if I can get control of my computer back again, I will move on from these movies so we don't have any more crashes. And this is why I didn't upload my talk. Okay, so let's move on to time resolution now. At the Center for Nanoscale Materials, we recently built an ultrafast electron microscope. So if you're doing electron microscopy, it's usually you apply a bias and you extract the electrons from the tip. If you want to go to faster time resolutions, there's nothing you can do there. So what you have to do, what I mean really fast, is femtoseconds. So if you want to get femtosecond electron pulses, you have to use femtosecond laser pulses in order to attain that. So we have this laser table set up here that is plumbed into our microscope by these two lines. There's some more laser breadboards here, and the microscope column has also been modified for these purposes. So from a schematic, what you have is those two lines that go into the microscope. One goes up to excite the photocathode. So if the laser is pulsing at femtosecond rate, you're going to get femtosecond rate electrons coming out. And the other laser goes to the specimen to excite the specimen in the way that you would like for the experiment. And so here's a little schematic of what happens. It's timed so that they meet at the specimen at the same time. So this photo excites the electrons, the fast electrons come down, and then you image your specimen just as you are exciting it with the laser. Here are just some statistics for the different kinds of things that our laser can do. We have the only ultrafast electron microscope as a user facility open to the public to come and use for free if your proposal is accepted through the proposal system. And we chose all of these different being able to go from basically 325 nanometers up to 1,000 nanometers in wavelength to be able to excite the specimen because we will have lots of different users. Recently, we have published two papers, one about the visualization of plasmonic couplings of a rod on carbon and how the plasmonic structure changes when it's near a carbon edge versus on a flat carbon graphene surface. And more recently, our publication in Nature on these chiral assemblies of pinwheel superlattices and the plasmonics surrounding that. We have another Nature paper that has been accepted for publication that I can't talk about today, but that's coming soon. So this microscope is producing a lot of good results. So here's just an example of how you can look at plasmonics as it changes with polarization, as well as if you set the polarization, it changes over time. So this movie is in picoseconds, and you can see that the plasmonic structure around these nanoparticles diminishes after 2 picoseconds or so. So what does this mean for catalysis? We're not going to be able to do the kinds of imaging that were talked about earlier in terms of atomic resolution imaging. So when we are in this stroboscopic regime that I have been talking about, we are getting about 1 nanometer spatial resolution and down to less than 1 picosecond. So we can get into like the 800 femtosecond type time resolution. This is great if your material is, if the process that you're looking at is a completely reversible process and the sample relaxes in the time frame that we are pulsing it with the laser. Many of our catalysis projects do not involve reversible processes. They are things that happen over time that we'd like to observe as time goes on. So here, when I talk about single shot dynamic TEM, it is for irreversible processes, but this means that you photo excite the cathode again, but with a lot of electrons coming down at once, like 10 to the 8, 10 to the 10. And so what happens when electrons are next to each other, they don't like each other, they repel. And so they repel as they're moving down the column. and that messes up our time and spatial resolution. So that's why we're over here in the nanosecond, microsecond regime and micrometer, nanometer, tens of nanometers kind of spatial resolution. So what we are working on at the CNM is creating a suite of microscopes that will be able to look at materials such as the ones that I've shown in a reversible manner at the hundreds of femtoseconds time resolution with about 1 nanometer spatial resolution, but also to go in the microsecond and nanosecond time resolutions, getting down to hundreds of picosecond time resolutions, but with closer to atomic resolution. So the UEM is the instrument I've been talking about that was installed in 2019 and is just, after it's really difficult to operate with the laser coming into the microscope. We have a Spectra 200 that is just a probe-corrected instrument that was very recently installed, but it does have these things here. I know that the writing is kind of small, but it also has a biprism, it has an MPAT detector, etc. The two new microscopes that we're getting, the one that's being installed right now as we speak, is this Spectra 300 instrument. And this has a beam blanker and an ultrafast pulsar. So this should, and it has a probe corrector. So we are hoping to be able to get atomic resolution with nanosecond, hundreds of picosecond time resolution. It also has a cathodoluminescence and photoluminescence system in it, initially purchased to be able to do quantum information science type work, but could be applicable to many other things as well. And finally, this last instrument that will be coming early next year also has a beam blanker, has double aberration correctors and high speed system. So this will be kind of our microsecond time frame. So we are hoping that we should be able to look at some of these catalytic processes with atomic resolution, with faster time resolution, and maybe we'll be able to see your moving atoms and see what those guys are doing. So just a plug before I finish, we are one of 5 nanoscale science research centers across the nation. And as I mentioned, we focus our electron microscopy on dynamics as well as all of the other standard electron microscopy. We have a lot of other things as well. We have a 17,000 square foot clean room. We have synthesis, nanofabrication, we have theory and modeling, we have our own high performance computing cluster. And we are the only nanocenter that has a hard X-ray nanoprobe beamline that we co-operate with the Advanced Photon Source. So if you are interested, please feel free to email me. Again, all you have to do is write a proposal. It's a little 2-page proposal. It goes through a peer review process, and then you're able to come and use the facilities and get the expertise for free. You just have to pay for your own travel costs. You can check us out at our website. I want to thank my collaborators, thank Heikwa and Tom for the UEM work. And with that, I will stop and take questions. Thank you.
Start. Actually, while I walk, is the ultrafast similar to kind of pump probe experiments done at the free electron lasers?
Yes, it is similar. It's different accelerating voltages.
Thank you very much. I appreciate very well your presentation. Nice presentation. In your example that you shows changes in the distribution of cobalt on the alumina when you reduce. My question is at which temperature you reduce? Because if the temperature of reduction is higher than 600 degrees, the cobalt aluminate is reduced and go to the surface. And you can detect particles of cobalt, metallic cobalt on the surface. Thank you.
Yeah, I didn't understand everything that you said, but I think you're saying what you were asking, what is the temperature that we used for that reduction?
Yes.
And it was 400 degrees C. Thank you.
Hello, very nice talk. Here, to your left.
Okay, thank you.
Yeah, very nice talk. In the first part of your talk, you mentioned how you can use these 3D tomography images to identify the changes in the cobalt size and distribution. So I was also wondering, with the same technique, is it possible to also identify the change in oxidation state of the cobalt? Because you see that in the reduction process. Do you see some changes in the images when the oxidation state of cobalt changes?
So, you mean like the oxidation state?
Yes, oxidation state of cobalt. Is that reflected in the images? The change in oxidation state?
You can't do it with this method, but if you use something like EELS spectrum imaging or possibly EDX mapping, you can do it. I have an example that I didn't have time to show here of EDX mapping 3D tomography. But it's harder and you need things to be stable because you need to take maps for longer at each tilt angle. You don't just take one image, you have to take a 5-minute map or something, whether it's EDX or EELS, to have enough signal. And then you need to accumulate all of those images to get the 3D image of it. But it is possible.
Okay, thank you.
Anyone else?
Lunchtime.
You said it. Let's thank our speaker one more time and all other presenters today. And thank you to the guys in the back helping with all the electronics.